question. Oh,
Let me record that, okay?
okay. My first question was, I was trying to figure out what is causing the EMF. Going back to that idea, and is it? And I'm thinking about how it's the moving charges that are creating the magnetic field, but is it the acceleration of the current that is creating the EMF? Is that
No, the EMF, well, actually maybe good time to share my phone again. I'll show you in kind of equation form and in picture form.
I guess I was trying to like if you were to have a slow motion situation of that magnetic field building
Uh-huh.
up and then just trying to picture that in my mind. I was just wanted to make sure I had that all.
Right. Okay, so let's see if I could draw maybe the inductor. Maybe the wire would come in, and maybe so I can get some kind of feel for 3 dimensions. Let me have like a core where if I put the wire over the top and then around behind, dot, 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 then over the top and down behind, dot, 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 dot. Okay. Dot, 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 dot. Okay, so let's say this is the kind of the flow of the current. And then for a cross-sectional view, let me take this front and do this. And let's see if I can get the picture right. So if I could see this wire in a front view, I guess it would come over the top like this and wrap around. Let me just stop it there to keep the picture simple. Okay. And so this is supposed to be the front view of it. But the phrase I like to use, and I started using it right at the beginning when we got to Faraday's law, but Faraday's law doesn't do it justice. I said that a changing magnetic field makes an electric field. And sadly, when I write this equation, you don't even see magnetic field in the equation, and you don't see electric field. So this is written, I think, a little better when you write it as I did in chapter 34 here at the end, where if we kind of ignore the number of loops for a moment, we'll put a minus, and then we take the derivative and we write it as a magnetic field. Okay, so that shows up a little bit better. Then on the other side, we write the EMF as an integral of an electric field. And that's going to be the key step, because what I keep saying is a changing, there it is, changing magnetic field makes an electric field. Because if you apply Stokes' theorem to this, this says that the curl of the electric field then added up over an area would equal to negative, and then if you put the time derivative in there, you can write it as a partial. But since these now become integrals over the same area, you see it a little better. And I don't want to do too much of the math, because I don't think that's really going to help you. And that's really not kind of what you were asking. But I want to convince you that this equation that I keep saying a change in magnetic field, looks better this way, change in magnetic field, makes an electric field. Now, of course, if you integrate the electric field over space, you get voltage, and if you integrate the magnetic field over space, you get flux. So that's why this equation is really the same as this equation. But I want to come back to the picture. And in the picture, if I was doing magnetic fields here, so I'll do the green, the currents that comes through and over and around, so if I use my right hand rule and I put the current this way, I would say that in this inductor, I have a magnetic field that goes down the core of it. This is what you would call a solenoid. This is really chapter 30.
Yeah.
But if the current is changing, and so, sorry, it's taking me a while to get here, but finally, if I say that this current is changing, then it makes a changing magnetic field. And according to this equation, a changing magnetic field makes a curl of an electric field. Now, curl means a circular part. So if I change to the color, what have we been using for electric field? I think kind of this burnt orange. Then what would happen as I'm looking down the core is there would be an electric field that would be in a curl, a circle. So trying to draw it here in 3 dimensions kind of hard, but it would come over the top and around like this. Over the top and around, over the top and around. And this electric field would be in the core. It would also be on the outside. But here's the magical point. It would also be right here in the wires opposing the current. And so there is an electric field. And so I think your question was trying to conceptually understand where do you get this EMF? And I'm trying to say all EMFs come from an electric field. So where do you get the electric field? An electric field has to be pointing in the direction of the wire in order to be an EMF, and that's how we get it. So the straight magnetic field, because it is changing, makes a curled electric field. And so this electric field then is pointing opposite of the direction the current is trying to increase, and that's our EMF. And so when you had a battery, we had charges. When we had a capacitor, we had charges. Both of these made an electric field, which then when we integrated the electric field, we called it a voltage. And hopefully what you get out of chapter 34 is the final conclusion of this semester that there are 2 ways to make an electric field. The first one is with charges, and that's what we've been doing up until this chapter. We have been making electric field with charges. We would take something like a capacitor and we would make one side of the capacitor positive and the other side negative. And if we drew a field in here, we would say there is an electric field. And if we integrated the electric field, we would say there is a voltage on this capacitor. So we've been saying that voltages, that is EMFs, are coming from the charges. Inside a battery, we didn't really study too much about the inside of the battery because the inside of the battery got pretty complicated and was more about chemistry than it was about the physics. But I wanted to emphasize that there would be a bunch of pluses and a bunch of minuses. Let's just take like a lead acid battery. There would be a chemical reaction between the lead oxide, the sulfuric acid, and the water. And so you would get an electric field. And I'm trying to say the same thing here, that I would get an electric field. But this is a harder to understand electric field. This is an electric field that is created by the changing magnetic field. And to be a EMF then, the electric field would have to be in the direction of the wire, which is why it's the curl. The changing magnetic field makes the curl.
Okay.
Yeah. if that helped. So there is an electric field. Um, you I don't know if you want to call it a secondary electric field, because it is made from a magnetic field, so there is no other additional electric field. So it's kind of funny to call it a secondary, but it is a secondary effect. It's the current that makes the magnetic field, and if the current is changing, the magnetic field is changing. If that magnetic field changes, you make an electric field, and if that electric field is created in such a way that it's opposite of the current, then it would be making a back EMF.
Okay, so when I was saying the acceleration of the current, what I was thinking is once that that current becomes constant, that the magnetic field becomes constant, and therefore the EMF is no longer generated. But
Right.
but what is promoting that during that period before that current reaches the constant?
Mm-hmm.
What is taking place there that is causing the change in the magnetic field, which therefore creates the
Okay. So the whole circuit would look like this. You would have the battery, and for the sake of discussion, I'll just say, let's say it's 20 volts. And then you would have maybe the switch. Okay, so here's the switch. Then you would have maybe the resistor and then the inductor. So R and then L. Okay. So when you first go to close the switch, the current is trying to increase, which then means the magnetic field is increasing, which then means the curl, this is the secondary magnetic field, electric field, excuse me. Does that orange stand out enough?
Yeah. So then the curl is creating the electric field.
Yeah. So at this point, there is an electric field. And as you pointed out, I think before the break, this electric field that is created from the changing magnetic field, which is created from the changing of the current, would at first create 20 volts. Okay.
So what I was saying is when you said the current is trying to go through,
yeah,
that's what I was trying to say by an acceleration of current. Like its velocity is changing, I guess.
Okay. Yeah. I think that's a fair statement because electric fields do put forces, and forces do put acceleration. So I think it's a fair statement then to say, in terms of acceleration, that if you looked at a little electron right here, it's being pushed from this force, and it's also being pushed equal and opposite by this force. And so at least at that moment, I would say the acceleration is 0. However, this is the part that I think was your time factor, is that, let's see if I can say this right. At first, there would be no current. So if I made a plot of current versus time, there would be no current. Right when I close the switch at 0, there's still no current. But there's 0 current, not because the switch is open, but because when I close the switch, there's a balance of an EMF from the battery and a back EMF from the inductor. However, and this is important, the current would be in the process of changing. See, because you only get the EMF while there is a change in the current.
Yeah.
So the current would be kind of sloped upward. So a moment later, there would be current. Let's just say there's a small amount of current, so that the current creates a voltage of 1 volt on the resistor. So there's not much current, but there's enough current to create a voltage of 1 volt. What that would do then is essentially say that this now has lost some of its punch, if you will. It lost 1 volt. So this one here, 20 minus 1, is only pushing with 19. So this will now push back with 19. And so it will have a change that is a little bit less. If you wanted to call it force, fine, less of a force. But it would still, not sure if I'm answering your question here, but it would be changing at a lower rate to justify the fact that we've got a lower voltage this has to be equal to. And then it would continue with that process that the current then goes up. And so instead of being 1 volt, a moment later, this is 2 volts. So instead of this being 19, this is 18.
And then eventually
And so
it levels out and your EMF goes away because your magnetic field is constant.
Right. So eventually this keeps climbing and this keeps dropping. And as you said, eventually we would get to 20, which means this would be pushing back at 0, and 0 volts means no change. And so it's a constant, and then it just remains that way.
Okay, and that's why you can treat it like a wire, because there's no resistance coming from
Yeah, right. So that's why we would say after a long period of time, you could just treat the inductor as a wire.
Awesome. Thank you so much.
Yeah. Okay.
I think my other question was just a little thing. We don't have to go too in depth into it, but I was noticing when you have a inductor charging, I guess, not, I know that's not really the right word, but
yeah, I prefer the word energize, but okay.
Energizing, you have your equation is a little bit different than when it's decaying. So I was just curious where that 1 comes from in the equations. So where you have I of t equals the I naught, or V over R, times the 1 minus e to the negative t.
Okay. Let me maybe. Well, you said not to get too much. Okay. So
I think some other people had some questions. I don't want to take too much of your time.
Okay. All right. So okay, let me split my paper in half. If I was energizing it, so I would have a battery, and then I would have this resistor, and then the inductor. And if I wrote out the equation for this loop, I would go V minus I R minus L d I dt equals 0. Now, if it was already energized, kind of like right before the break, we were talking about something that might look like this, where you had a switch, you ran it through resistor 1, but then that split off to an inductor and a resistor number 2. And if you left the switch closed for a long time, eventually all the current would be going through this inductor. So the current would have an I, I'll call it I naught, because it would be this V divided by R1. So that when you de-energized it, that is when you open the switch, the current would continue to go around this loop. And we wrote that as minus L di dt, and then plus, let's see, well, if it started to go around this way, I guess it's minus IR2 equals 0. But here's what I'm getting at. If I eventually solve And then since you were saying don't go through all of it, so okay, so I won't. But if I were to do a separation of variables, I would get a di on this side of the equation. And then over here, if I did a separation of variables, I'd get a di also over here. Maybe I better write out a little bit more. This would look like an I over it. Let's see, when I move this over, this would be R2 over L with a negative. But this over here, let's see, if I move this to the other side and then divide, I get a V minus I R. I get an L. But here's what I'm getting at is when I integrate, my limits are different. We'll see if this helps. On this one, at 0 time, we would start with 0 current. But on this one, when we integrate, so we've got a dt, at 0 time, we would actually be starting with current I naught. So you would have ln of I evaluated from I naught to some other current, whereas over here, you would have ln of blah, 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 and you would be evaluating from 0 to I. And that's where the math comes in different. The beginning situations, what you would call the initial condition.
Mm.
And when you put in your limits of 0, you get different than putting in your limit of I naught.
Okay, cool. Yeah, that helps me a lot. I think I can read math a little better now.
Yeah, which is why then on this side of the equation, when you actually go through all the math, you get an I naught and then a decaying exponential. Whereas this one, when you go through all the math, you get I equals, and it's building up, so you get an I naught. And then as you said, you get that 1 minus the decaying exponential. But it's actually that 0 right there that makes the difference between these two.
Okay, cool. Thank you. Yeah, that helps a lot. I think Gina has a question for you.
Okay. Let's see, chat room here. Oh, I don't want to do that. Let me. All right. So hope that helped. Let's here. Oh, looks like Daniel's a little bit here before Gina. So chapter 34, number 12. All right, let me write that down. Chapter 34, number 12 at 12:55. Okay. So put here. So chapter 34, number 12, page 1 here. And I need to look at that PDF for 34. Scroll down to number 12. Now be careful with this wording. I was helping somebody else, and they kind of missed that first word. It says verify by substitution that the following equations are solutions to equation, I need to look these up, 34.15 and 34.16. And I think those are the two differential equations that kind of cross-connect electric fields and magnetic fields. But let me go to the textbook here. All right, so here's the textbook. Let me call it up. Let's see, chapter 34, and then equation 15. So equation 15, oh no, it's not the one I was thinking of, is the wave equation. That says that the second derivative of the electric field with respect to space is equal to mu naught over mu naught times epsilon naught. So permittivity times permeability, or permeability times permittivity. And then the second derivative of the electric field. And then and that one I worked out in the lecture. I didn't bother to do the reverse substitution, but that would say that there is also an equation for the magnetic field, which has to follow this pattern. And I hope what I somewhat got across to you, because this was my comment, that this got very exciting for Maxwell. When Maxwell saw this, he knew this was a solution to a wave. He knew it would be a solution of some function that would then be of some value. And this particular problem, the function happens to be sine waves, okay? But it doesn't matter what kind of function it is, and it moves along, and it moves along with a certain speed over time. And so and I digress a little bit from the problem, but I want to emphasize that what got Maxwell excited after he added his term, his displacement term, and he, goes through the equations and he eliminates, say, the magnetic field, so he gets this one, or he eliminates the electric field and he gets that one. He says, well, what kind of functions are the solution to things like this? And he realizes that things that have the same shape but then move along, having that same shape a little bit later, which we call waves, fit it. And so I was trying to show you that this is the solution to the wave. Now, we don't have to do all of that. We just have to confirm that if the electric field follows this form, it has some maximum value, call it its amplitude, and it has a cosine of a k and x minus omega t, then this is the solution to that. And I wanted to emphasize, notice the question says verify. So you don't need to solve this differential equation and show that this is one of many solutions. What you have to do is show that this is just one of many solutions by taking it and putting it in here. So let's give it a try. So let me do the left-hand side of the equation. The left-hand side of the equation says if you take the derivative twice, what do you get? So let me take the derivative twice. So as I look at this and I take the derivative the first time, the maximum would stay the same, and the derivative of a cosine is a negative sign. And then, of course, the chain rule would then give me a k out in front. So that's the first derivative. So let me take the derivative yet again. So all of this would remain the same. But when I take the derivative of sine, I now would get cosine. Is that right? Well, yeah. And then the chain rule would give me another k. All right, so I would say that is putting this equation into the left-hand side. Let me try the right-hand side of the equation. Okay.
Would these type of questions be on the test or no?
I probably not. I mean, I don't think there's a whole lot of insight to the physics here of verifying this as a solution. And there's one piece coming up that you may or may not be familiar with. So I wouldn't like it as a test question. You'll see that in a minute here.
Okay.
But let me go ahead and do the right-hand side. So the right-hand side already has the permeability and permittivity of free space. And then it says take the second derivative with respect to time twice. Okay, so let me do that same kind of thinking. And if I took the first derivative, the constant, the amplitude just stays the same, but the derivative of a cosine is a sine, and then the chain rule, since I'm doing it with respect to time, would, oh, wait a minute, I might have said that
It'd be a
wrong.
negative sign.
Yeah, I was thinking there should be a negative here, shouldn't there? Derivative of cosine should be a negative, so let me put a negative out there. Yeah, so negative sign. And then the chain rule will give me a negative omega. Now, let me take the derivative then a second time, and maybe I should have wrote this on 2 lines. I did the same thing up here. But if I take the derivative of this, all that stays the same, and the derivative of a sine becomes a cosine. And the chain rule gives me another negative omega, so I'll just put a little square right there. So again, trying to verify this, I'm trying to say, does the left-hand side equal the right-hand side? All right, well, let me write out the left-hand side. So on the left-hand side, I get a minus k squared.
Real quick,
Yeah.
before you get too far,
Yeah.
where you have under the right-hand side of the mu naught e naught, and then parentheses, is that just a negative inside the parentheses? The first one, to your left, there.
Oh, yeah, that's a -1.
Okay, I was just wondering. It's like, is that just a dash, or am I missing something?
Yeah, no, it's kind of a cheater's way of writing a bunch of negative signs. You just put a negative and ones are just kind of implied.
Okay,
Yeah.
thanks. Sorry.
I should have. Yeah, and you might not be used to that. That's not normal till upper division. Okay, so I'm gonna write what I got for the left-hand side. So I got the negative k squared e, and then cosine, and I'll just save a little writing by saying it's cosine of gobbledygook. Because the right-hand side is a mu naught, epsilon naught. There's the negative. I'll put the negative out in front. There's the omega squared. There's the electric field. And there's cosine of gobbledygook again. All right, so there's the question, does it work? Does the left-hand side match the right-hand side? Well, I'll just start canceling off cosine of gobbledygook, okay. Maximum electric field, okay. Even the negatives. And so what I'm left with after that cancellation is k squared equals to mu naught epsilon naught times omega squared. Okay, so if that is true, then yes, the left-hand side does equal the right-hand side. But I still have this question: is that true? Well, it is, but I need to show you that. The speed of these electromagnetic waves is what that is. That is 1 over the speed squared. So this mu naught times epsilon naught would be 1 over c squared, and then we would have this omega squared and this k squared. Okay, now is that true? Well, it is. You may not be familiar with it though, so let me do a couple of things. The first one I know you are familiar with, and that is I can take the square root of both. Okay. The other thing I know you're familiar with is the omega. The omega is 2 pi times the frequency. The thing you may not be familiar with is this k. What is meant by k in this equation? So let me come back and do a little bit of trigonometry here. If I were to write or draw, I guess I should say, a sinusoidal wave. So let me write it as K. I'm sorry, let me write it as sine. If I just wrote it as sine X, and so this is the x-axis and this is the y-axis, and so y equals sine X. You would have said to me, well, the sine function repeats itself in 2 pi. Okay. So mathematically, how do I draw or calculate something that has a different wavelength? In other words, how do I make something compress on the x-axis or expand on the x-axis? And so we've got to go back to our algebra class from that and realize we would have to put a multiplying factor in front of the x. So if I put something in front, let me just put a box for right now, times x. This would allow me mathematically to adjust for different size wavelengths. I could have either big wavelengths or small wavelengths. If I just left it as x, the only wavelength I could have is 2 pi. That's what the trig function says. The trig function says it repeats itself in 2 pi. But to expand things on the x-axis, I have to have a multiplication factor. Now, that multiplication factor is what this problem is referring to as the k. So coming back to our original problem, that's why they have a k in here. This k then would allow for our waves to have multiple different wavelengths. If you only had an x here, then you would say, well, this only allows for a wavelength of 2 pi. All right, also focusing on algebra for a moment here. This k, as I said, is related to the wavelength lambda. But how is it? Well, remember our trig functions repeat every 2 pi. So if you want this to be one wavelength, so in other words, for x, you're going to put in 2 pi, and you want this whole thing to come out. I'm sorry, I said that terribly wrong. Let me try that again. All right. You want the whole thing here to come out to be one wavelength. Okay. I'm gonna try this again. I'm not saying my mouth very well. Apologize here. All right, let me try it again. When you go along the x-axis, and when you go one wavelength, so the one I've drawn in blue, green. When I draw this in green, when I get right here, and so when x is equal to one wavelength, I want this whole trig function to be 2 pi. So what I'm trying to say is when I take k and I multiply it by one wavelength, I want that to be 2 pi. That's when a trig function repeats itself, when the whole thing gets to 2 pi. So at one wavelength, multiplied by this multiplication factor called k, it's got to be equal to pi. What I'm trying to get you to see then is k is related to the wavelength by this equation. That's why we put that multiplication factor into our mathematics, so we can stretch or compress it. And k's got to be related to the wavelength. How is it related to the wavelength? This is how. So if we come back to this equation we were doing earlier, we had k is equal to 2 pi times the frequency over c. K then has to be equal to 2 pi over lambda. So again, we're back to this question, is this even true? You know, does the left hand equal the right hand side? And we said, yes, it is, if that's true, which is if that's true, which is if that's true. And so now we're at this point, is this true? And this is where we get to something we can confirm that, yes, it is true, because the 2 pi's cancel off. And then we take wavelength times frequency and we get speed. Is that true? And the answer is overwhelmingly yes. So when you take wavelength times the frequency, you get the speed. Maybe I should emphasize that I worked that out in the lecture. So we know this is true, which is why I needed to figure out what K was in terms of wavelength, so I could get back here and then ultimately say, yes, the right-hand side does equal the left-hand side. But there's 2 things that, two, as you asked earlier, 2 big things, which I would say doesn't make it a good test question. The first one is, we're not really doing any physics. We're just verifying that this math works out right. Okay. I would rather do something, and this would be too much to ask, but I'd rather say solve this equation, not here's the answer, verify it, put it back in. That's plug and chug stuff. So no, that doesn't make a good test question. And then likewise, another thing that probably doesn't make a good test question is because this K, a number of people are going to get stuck on this. They don't know what the K is, and you got to think about it quite a bit, and it becomes more of a math question. How do you stretch something and compress something? And although I do like this step where you factor of a K, and then here's where you got to kind of read the math and realize that the K has to be 2 pi over lambda. So that's a nice piece of the puzzle.
Is that
it's also not a fair.
Sorry.
Go ahead.
Is that formula you derived for K a general equation for K? Or will it like vary with like different factors and different shapes?
It would be true only for sines and cosines, because sines and cosines repeat themselves every 2 pi.
Okay, but not like a tangent function or something
Right.
like that.
Tangent repeats itself every pi, so yeah.
Okay.
Yeah. So it is kind of limited to what we call sinusoidal and cosinusoidal waves.
Mhm.
It also is not a fair test question because this discussion that I just did is a discussion we have in Physics 123, and half of you have had that discussion and half of you have not. So for half, and you're one of them who has not, if I'm recalling right. Yeah, you were.
Yeah, I'm taking 123 in spring.
Yeah. So maybe I should say, remember this discussion, because you're going to see it in chapter 6. 15, 16. I believe it's 16. So it's the second chapter. So we'll start in chapter 15 and then do 16, and we'll have this discussion again in late January.
Cool.
Yeah. Do you want me to do the magnetic field, or you got the idea that it's going to be the same thing?
Yeah, I got the idea that it's.
Yeah, see, because you're going to get everything. It's going to be exactly the same. You're going to take the second derivative. It's just right here, you'll have magnetic field. And magnetic field. So you'll just have magnetic field on each side that you'll cancel.
It's basically the exact same steps, but instead of electric field, magnetic field.
Yeah, yeah. Which again is why we call these electromagnetic waves, because everything the electric field is doing, the magnetic field is also doing. They go hand in hand. Which,
Okay.
by the way, talking about next semester, when we get into optics, which I hope what you caught in chapter 34 is a special case of electromagnetic waves is the visible part of the spectrum. And so when we get into chapter 35, well, we start optics in 35, and you can see why it's 35, because 34 here is where we get Maxwell's equations and we get to the whole electromagnetic spectrum. And so it's just a natural fit to start talking about a special case of electromagnetic waves, and that's optics. So 35 is about optics. We'll probably do that about April. 36 is also about optics, but both of those don't really get into the wave nature. It's not till chapters 37. So 37 and 38, we will start drawing our optics as waves, and I'll start making these squiggly lines. So keep this in mind. And I'll say, oh, let this represent the electrical field. And I won't even bother to try to draw the magnetic field. I'll just say, remember that the magnetic field is then perpendicular. And if I try to draw it, I think it gets kind of messy and hard to see. But that's supposed to be the magnetic field perpendicular to the electric field. And whatever the magnetic field is doing, or excuse me, whatever the electric field is doing, the magnetic field is doing. So we just don't draw it. We just say, hey, it's obvious. But I don't know if that's so obvious until I emphasize it now. So, good. Oh, hey, my camera froze again. Doing a lot lately of that today. Wonder why. It's not my screen. Can't recall me doing anything different here. But I'll reconnect it and see where we go. All right, well, like I said, hopefully that one was a little bit enlightening in terms of it. Yeah, it does work. In fact, this is that part of that lecture, if you got a chance to see it all, where I kept saying, hey, there's a lot of math here. Don't worry too much about all this complicated math. I would rather you just kind of get the conclusion as we come to the end here, not so much understand that wave equation and where I got it.
Thank you.
So let me bounce back over to the Zoom here, and off to Gina's question here. All right, so Gina's got one from 34, number 25, and the time is 1:19. Okay, so let's come back here to that same set of questions. Number 25, where's 25? Ah, here we go. So chapter 34, number 25, and let me read it here. High-powered lasers in factories are used to cut through cloth and metals. Oh, this is fascinating. Boy, if we had field trips, to see the laser replace like a saw blade or a mill machine is amazing. But you know, I've seen them take like these stacks of plywood, and they'll just be like, you know, 5 layers thick of plywood, and then this laser beam just blasts through, and it just carves out this path, and then that's your whatever they're trying to make. Let's say a model boat. I've seen them do this with kits to make model boats, and they just take that plywood and just zap through it. It's amazing to see these things cut. And in fact, one of my dad's friends, well, I guess this wasn't a laser, or never mind, because another way they do it, that instead of a high-powered laser is a water jet. That's even neat to see too. Just this water, a beam of water just cut through the plywood like it's melted butter. It's bizarre, but he worked on these high-pressure hydraulic systems, and it had a pin leak, and it was shooting out the side, and he put his arm right through it, and it just cut right to the bone, just like a laser. I mean, well, I like a laser, but just like a giant sharp knife, just cut it straight to the bone, all the ligaments, everything. It's just amazing how these high-powered either lasers or high-powered jets of, in this case, hydraulic fluid, can can use. Anyways, I digress here. Let me keep reading here. So one such laser has a diameter of 1 millimeter and generates an electric field having an amplitude of 0.7 megavolts per meter at the target. Find A, the amplitude of the magnetic field. Okay, so let me say something and extra emphasize that the ratio between the electric and the magnetic field is the value of C. That was what I was trying to show in all that complicated math. And so I'm going to say it again for you guys, that if you didn't follow all that complicated math, that's not a problem. That's not the issue. There was one equation that looked like this after I did the curl. It said that the derivative of the electric field in the x direction is equal to negative the derivative of the magnetic field in the time direction. Okay. Now, remember that actually followed the equation we were just doing, where the second derivative of the electric field with respect to space equals mu naught times epsilon naught times the second derivative of the electric field with respect to time. So it's because of this equation, we know that one solution, as we just proved, was equal to the maximum times the sine of kx minus omega t. So that was the problem we just did. Now, if you then take this and put it into here, you can show that this is true. So maybe I shouldn't even have taken that time because, again, I don't necessarily want you to go through and redo all of them. I just wanted to say that you could do it, and I did it for you. Did it kind of rushed there at the end, but an important piece to realize is there is a mathematical connection between the electric field and the magnetic field. Now, let me give you a word of warning. This is only true for electrics and magnetic fields that are created from each other. And let me say it again. Remember that in chapter 34, I was trying to draw the conclusion that there are two ways to make an electric field. One way is from the charges, and another way is from a changing, if you let me use delta, magnetic field. So if your electric field is made from charges, if we go way back to the beginning of this semester in chapter 23, and we just take, say, a proton that has a charge of 1.602 times 10 to the minus 19 coulombs, and we say, what is the electric field over here when you're, say, 1 centimeter away, you would use Coulomb's law that says it's 1 over 4 pi epsilon naught times Q over R. That's how you would get the electric field. But that wouldn't create a magnetic field. There's not a mathematical connection between the electric and the magnetic field for this. The connection between the electric field and the magnetic field is where you only have case number 2 involved, where an electric field makes a magnetic field, or I should say a changing electric field makes a magnetic field. Then that magnetic field is changing, so that changing magnetic field makes a new electric field, and that electric field is changing, and that new one makes a magnetic field. So I want to emphasize that there is a mathematical connection between the electric and the magnetic field, but only in the case where these things are created from the changing, not these other cases. So if you had a solenoid and you said, what's the magnetic field from a solenoid or a toroid? That's made from the current. That has nothing to do with the electric field. You couldn't use this relationship for the solenoid or for the toroid or for the wire or for the point charge or for the capacitor. Okay, you could only use it for the electromagnetic waves. And so I want to emphasize that because I have seen that, sadly, well, more on the final than on the test 3, because on the final, there is often this question such as, what is, and we go all the way back to the beginning of the semester on the final and say, okay, what is the charge 1 centimeter from a proton? And then for some reason, people do that correctly, but then they calculate the magnetic field using this relationship, and that's a big no-no because this is the relationship for electromagnetic waves. This is not true for what we've done most of the semester, which is getting the electric field by either charges or getting the magnetic field from conventional current. This is only true for this last particular step of that you don't have charges around, you don't have current around, yet you have electromagnetic fields themselves. So that was probably too much words. I guess I probably shouldn't have said all that, but I just wanted to help you out that you do know the connection between the electric and magnetic field for the case of electromagnetic waves. And that's what we have in this problem. So I'm going to use that to my advantage and come back to the question and say, A, what is the amplitude of the magnetic field? So if I rewrite this, I would say the magnetic field then is equal to the electric field divided by the speed of electromagnetic waves. So this is 0.700 times 10 to the 6 volts per meter. And then this is 3 times 10 to the 8 meters per second. And then grabbing a calculator, 0.7 times 10 to the 6th divided by 3 times 10 to the 8th comes out to be 0.00233. And this should be Teslas for the unit of the magnetic field. Maybe I should just confirm that because this right here would be a volt over a meter. And then when I flip this, this would be second over a meter. Let's see, a volt is a joule per coulomb. And a joule is a Newton times a meter. And so one of those would cancel off. And our definition of a Tesla is right here, that it is the force you would get when 1 coulomb is moving at 1 meter per second. So yes, it does work out to be Tesla. All right, so again, hopefully didn't bore you too much by going through and figuring out what it is in the Teslas, but that's really all there is to this problem. I guess that's why it's a black problem. All you gotta do is take the electric field and divide by the speed of light. Everything else I was saying was just extra stuff that will hopefully clear your mind of any confusion. All right, so there's A, and looks like there's a B part of this. Okay, so page 2.
Could you put that last bit up?
What about the last one? What?
The last bit where you're converting the unit, just to verify.
Yeah. You want to see it, or you got a question?
I did want to see it, that's all. All right.
Okay. All right. Good. Okay, then coming over here to B. B says the intensity of the laser. Now, the intensity is the energy density times the speed. And I hope I didn't do this too rushed. I was working along on that lecture of 34 on Tuesday and realizing that I'd probably spent too much time on the advanced math, and I was, anyways, and that's why I stopped short of section 5. But in the ending part there, I derived the energy density by saying the energy density would be, some of it would be made of the electric field and some of it would be made of the magnetic field. And since the strength of the magnetic field is connected to the strength of the electric field, you could write this all in terms of the strength of the electric field. So that was our conclusion. And so that's what we'll just kind of plug and chug into here. This is 1/2. This is 8.85 times 10 to the minus 12. This is the electric field, which is the 0.7 times, was it mega? Yeah, mega. We'll square that. And then this is the speed. And so the intensity of this laser beam, it makes sense, it's related to the strength of the electric field, because the intensity would be related to the energy, and the energy would be both electric and magnetic, and the magnetic is connected a little bit to the electric. So if I put this into my calculator, I'd have 0.5 times 8.85 times 10 to the negative 12 times 0.7 times 10 to the 6th, and that squared, times the speed of light, 3 times 10 to the 8th. Whoa. That's 12. Yeah, I guess that's right. And I know it's supposed to be big. Okay. 6.50 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then this is the intensity, so this would be watts in 1 square meter. That'd be a heck of a lot of energy in 1 square meter, but it's a little narrow beam. It's only 1 millimeter in diameter. So the intensity per square millimeter is, or square meter is huge.
Professor, the solutions online have I think it's the same answer, but I guess they're arranging it slightly different. Would you be able to compare the two and explain it?
I will try. How's that? Yes. Okay, yeah, let me jump over. Okay, so the solution online. Let me look at the solutions here. And what were we looking at? Number 25. Let me scroll down here. 20, 24, getting close. 25. Okay, so A, they divided by C. Let me just check A, and they got 2.33 millitesla. Okay, good. Oh, then they did 650. Oh, I see why it looks a little different. Okay, okay. Yeah, well, first of all, we got the same answer. This would be 650, and then times 10 to the 6th, which we can write as megawatts per square meter. So I did it this way. They did something like this. Watch this. They start with this equation. They don't write it. But then they play this little game. They multiply the top and bottom by C. Because C squared is 1 over mu naught epsilon naught. And so that was the other beauty of that wave equation. So your author replaces this C squared, and I'll just leave the first, or the C downstairs alone, but he replaces this this C squared with 1 over mu naught epsilon naught. So cancels off the epsilon. And then so across the top just has electric field squared. And across the bottom has the permeability of free space and the speed of light, and I. So this is where your author starts with that equation, which I can see why, because it's real just an easy step to then move to the other side, take the square roots, and get, oh no, I was gonna say if we were getting the electric field, that would make sense, but we're trying to get the intensity. So I'm not sure why that's a better advantage. But anyways, that's what he used. So.
Okay, perfect.
I think that's what you were after, yeah. And then I believe this one has a part C. Let's see, come back over here. Part C, so I did the intensity. Oh, then the power delivered. Okay, so then the intensity is the power over the area, or for part C, I'll just say power is intensity times the area. That's why I was saying earlier that this number was huge, because look at that. It's 650 million watts in square meter. If you had 1 square meter, if this laser beam was as big as a square meter, this, this would be, as much energy as a giant power plant making electricity for the city of Los Angeles. But it is a much lower power than that because the area is so much smaller. But I'll take the 6.50 times 10 to the 8th watts in 1 square meter. And then I will multiply it by the area of this laser beam. They don't say exactly that it's a cross section of a circle, but they do say it's a diameter. So let's take pi and then r squared, and they say the diameter is 1 millimeter, so this would be 0.001 meters cut in half and then squared, so that would be the area. So if I grab the calculator now and go 0.001 and divide it by 2, square that and multiply it by pi, that gives me the area. And I multiply that by 6.5 times 10 to the 8th. We've got a much more reasonable amount of power at about 510 watts. And that is not too much to ask. Usually these lasers are 10% efficient at the best, maybe 5%. So I'll go 5%. We multiply by 20. So you'd have to plug it into the wall and get about 10 kilowatts out of the wall, which is quite a bit, but not for a factory. Maybe quite a bit for a home. It'd be like 100 light bulbs. But nonetheless, you'd have an excellent cutting tool. And as long as I did call up the solutions, although where are they? Here they are. Let's see. They got 510 watts. Yeah, good. Nice. That was a good one.
Cool. Thank you very much.
All right. Okay, let's see. So let me go back here to the Zoom here. I think I saw another question after Gina's. All right, Anthony. All right. So let's try. Let's see. What number is this? This is chapter 31, number 67. And let me put a time of 1:41. And see if that makes any sense here. All right, so I'm going to write this on here. So chapter 31, number 67, and I'll go page 1. All right, so let me get to the questions again. And okay, chapter 31. where is chapter 31? Okay, here's 31. Okay, and so scroll down to 67. Okay, 67 says a long straight wire carries a current that is given by this equation. Okay, I've got more to read here, but I think I'm going to just make myself a long straight wire. Maybe I'll make the current. Oh, I should have put an arrow because it's sinusoidal. Okay, I'll do 2 arrows. But the current, as a function of time, is some maximum value, I max, and then sine omega t and a phase. So it's changing. Okay. The wire lies in the plane of a rectangular coil of n turns. Oh, as shown in figure 8. Oh, okay, let me jump to the textbook and go to chapter 31, figure 8. All right. I got active figure 8. Is that the same thing? Or let me come back.
Don't think so.
Figure 31. Oh, P31.8. Ah, P31's problem. My bad. I skipped over the P. And I usually, oh, this is our mistake. Usually we put that picture. What's the picture above it? That's for 66. Okay. My bad. So let me come back to the book. But yeah, let me scroll all the way down to the problem. Sorry about that. I don't know why we didn't copy it. Okay, so here's the picture they have. Now I'm really confused. '67. Okay, so it's, yeah, okay. I just wanted to look at 67, make sure I'm reading it. So it says number 8. So, okay, so let me scroll up to number 8 here, and I'll draw it on my piece of paper here. Oh, here. So here's what they have. They have then this wire that I have. Then they have a rectangle. I shouldn't have put my equation right there. But they said that the rectangle has a length L and a width W. And the distance away from the wire, I believe that's an H. That's 50%. Yeah, that's an H. Make that 100%. So that's an H. Okay. So I don't know if that was really your question, the picture or not, but I'll keep going here. And they say there are n turns. I'm going to put a little n in my diagram, but it says the wire. Let me just read it again. The wire lies in the plane of the rectangular coil of n turns, as shown in figure P31.8. The quantities I max, okay, so this quantity, omega, phi, are all constants. Determine the EMF induced in the coil by the magnetic field created from the current in the straight wire. You can assume that I max is 50. This is omega is 200 pi, n is 100. The width is 5 centimeters and the length is 20 centimeters. Okay, so I'll put in my numbers a little bit later here. But this whole chapter 31 was about Faraday's law, which says this is how you calculate the EMF. It's based upon the change in flux. So we need to look in the problem and say, okay, where is there a change in flux? And of course, this wire has a current that's changing. So if the current was going, as my thumb's pointing, which I guess is to the left, then the flux would be coming straight out. Now, a moment later, the current would be going to the right here. So I'm trying to hold my hand here to the right. And then the flux would be going in. So maybe my picture isn't very good because I show flux coming out and in. And I'm trying to say that's not at the same time. Those are different moments in time. Let me take off my sweatshirt. I stood up to get my right hand across here and realized I was getting kind of warm. Okay. So, all right. So the flux, though, is either coming out of the page or a moment later it's going into the page. But the real point is it's either coming out or in. And so the angle between the normal vector and the flux or the field is 0 degrees or 180 degrees. So
And that's from the current oscillation, right?
yeah,
Back goes up or down.
right.
Okay.
Right. Okay. And as I jump back to my video screen, it looks frozen.
Yeah, I think it is.
Bummer. Okay. I rebooted everything when we started today too, but I think I'll do it on the next break too. Just something keeps misconnecting. Okay. All right. So writing this out, you could either include or exclude the negative sign. I guess I'll just keep it there for a second. N is the number of turns in this secondary, which I think they do say take N to be 100. Okay, so I'll do that later on. This there is the derivative. And the flux is this integral of B dot dA. And that's where I'll just do the dot product. It'll be the magnitude of the field times dA. And that's where we can kind of get in this debate on what is the direction of the field. But it changes with time, so it doesn't really matter too much in terms of the magnitude of it. So I put a cosine of 0. Continuing on, but have to go back to chapter 30 and remember that the magnetic field from a wire, because that's where this magnetic field is then coming from. It's coming from this wire, so we're trying to figure out what the EMF is in this secondary, this rectangular loop, coming from this primary here. And then, of course, looking at this equation, we can see that the magnetic field would be strongest the closer you are to the wire and then get weaker. So strong here and weak here. So when we go to add it up, we probably want to take strips in this fashion, because a horizontal strip like this would all have the same strength of the magnetic field. And so imagine just chopping this into a bunch of strips and then adding up the flux in each strip. And since the field gets weaker out here, the further away we are from our primary wire, then the flux in this last little strip would be less than the flux in the first one. But we can write the area of that strip as L, the length of it, so this way, times its thickness, and in terms of calculus, I'll call that a dr. And so now I can look at what I have and start pulling things out. Mu naught is a constant not only in space but also time. So I'll pull the mu out all the way, not only in front of the integral, but in front of the derivative. Now, the current is a constant in space, but not time. See, the current changes with time. but in terms of space, it's got the same current here as here as here. So that tells me I can pull the current in front of the integral of space, because it's a constant in space, but it is not a constant in time. So I'll put it right here with the derivative of time. Now the L, the length of this, well, that doesn't change with time or with space. In other words, L is the same all the way up and down, so same with space. And a moment later, it's still the same L. So L is a constant in both space and time, so it can be pulled all the way out in front. 2 pi are clearly just numbers that don't change with space or with time. Now this right here, the R clearly is a variable of space. And so I'll do this and I'll get just space, which can then be pulled in front of the derivative because that's just the time. And so this right here would be the natural log evaluated from my first little strip, which would be at position H. And the last little strip would be at H plus the width, which would make ln of H plus W over H. Okay, going on to page 2. I would have then this equals negative n mu naught L over 2 pi. And as I said a moment ago, after I do this integral, it's a constant in time. It's once I've done the integral, that's it. I can put it in front of the time derivative. So this would be ln of H plus W over H. And now I have the derivative of the current. And so maybe I'll write out the equation for the current. Oh, sorry. The equation was a sign. I'm already thinking derivative. Okay, so that's the equation for the current. And so when I take its derivative, so minus n mu naught L 2 pi natural log H plus W over H. And then the time derivative, well, the maximum current is a constant. I can pull that out. Derivative of a sine is a cosine omega t plus phi. And then the, or is it a minus? Sine is cosine, okay. And then the chain rule gives me the omega. And so now they gave me all these parameters. Let's see, determine the induced. So n is 100. U naught is 4 pi times 10 to the negative 7. But again, I've got a 2 pi downstairs. So I'll just cancel to save a couple keystrokes on my calculator there. L, they say, is 20 centimeters. So I'm going to write it in terms of meters. This is the natural log. The H and the width W are each 5. So this would be 0.05 downstairs. And then when you add them together, that's 0.10. In fact, that is just 10 divided by 5. So that's a 2. I'll save myself some more keystrokes in a moment. Then I have the maximum currents. I thought I saw that somewhere. Oh, there it is. Oh, hard to read. Does that say 50 amps? Let's see if I can zoom in on that.
Yeah, I think it does say 50 amps.
Yeah, it is an A for amps. Okay. 50 amps. Okay. And then the omega is the 200 pi inverse seconds. And then I would have this cosine piece. And oops, I'm a little bit off the screen. Let me just say that that's going to be the same thing so I can get a number here. So I've got a negative, and then I'm going to get a number, and then I'm going to get this cosine of 200 pi t plus phi. And so there's the time part. So not a surprise that the induced EMF changes with time. Okay, but now I can grab my calculator and start punching in these numbers. So this is a 100 times, let's see, I canceled those. So this was 2 times 10 to the negative 7. This is a times a 0.2 times, this is a natural log of 2. This is times a 50. This is times a 200 times a pi, and I think that's everything. So 0.0871, and then the cosine. And so this would be the, and I guess units would be volts. So this is the EMF created in there. If they gave me the resistance, I could then do the current, but it doesn't look like they do that. Yay. And I should probably double check this with the solutions. See, we were doing chapter 34, so let's look at the solutions to 31, and I'll scroll down all the way, and they write it at, good, yeah, they go 87.1 millivolts. Mm-hmm. Nice.
Right. Yeah, thank you.
Nice. All right. And I wonder if I can, we'll see what the next problem is. I'll see if we can save a piece of paper here by putting that there. All right, let me jump back over here to the chats. Let's see, what did we just do? 67. Okay, okay, and then Gina took off. Okay, and then Zach. Let's look at chapter 33, number 65. Okay, and let me put it here. Chapter 33, number 65, at a time of 1:59. Oh, hey, 1:59. All right. Well, we'll make sure we finish this one up for you, Zach, but looks like it's going to be break time after this. Oh, good, it's the last question. So I'm sure you guys will have more for me at 3, so no worries there.
This one's kind of more of like a very specific version of one of the questions I was asking earlier. So I figured it'd be a good way to iron out that.
Good. Yeah, no, okay. Yeah, I agree. Okay. So let me get over to the questions again. I lost the questions. Where they go? Here we go. All right. So chapter 33, found it. Scroll down here to number 65. Oh, now 65 is okay. Okay.
It is kind of a lot, but
Well, here's the thing about 65. 65 has the resistor, the inductor, and the capacitor in parallel. They're not in series.
right.
Right. So this is a little, and so I want to say a couple of things. The first one is this would not be on the test. This is anything that's not completely just in series is what we went through. That was enough. This is a good one, though, because your author does something. I like this problem because it jumps into phasers. He uses the LCR series circuit to introduce you to phasers. Okay? And phasers can become a very, very powerful tool. And then he throws this at you. He throws them in parallel, because if you truly understand phasers, these three in parallels is actually really, really simple. But let me emphasize, it is a little beyond the intent of this class. This is, to be quite honest, this is more of an attempt to say, let's make you think one more step. I already, he's like saying here, I already showed you how to do phasers when they were in series. Can you extend that and do them in parallel?
Okay. Yeah. Because, I mean, if this is as complex as you're kind of making it to be, maybe this would be something better to do as its own standalone video, rather than part of this. If that's.
Oh, actually, I like that. That's a good idea.
Because that way, I mean, I could still get it and learn from it.
Yeah.
Yeah. And that way, if we wanted to go break a little sooner, we could all do that.
Okay. Well. Okay. Yeah. Let's do this since it's a little after 2. Let's call this a break. We'll come back at 3. If nobody's around at 3, then I'll do it, and that'll become the video. If there are questions more specifically towards something that's not, that is an extension beyond this class, but this is a really good problem. And so it's why I signed it for the homework. And so it makes a good homework problem, but not really a good test question. But I will definitely do it. And so if there's no other questions, we'll do it at the next break. Other than that, I'll do it this evening and make a standalone video. Yeah.
Okay. Yeah, that sounds very reasonable.
All right. Cool. All right. So with that in mind, I guess I'll grab something to eat here, stretch my legs, and see you guys in an hour.
Okay. All right. We'll see you in a while then.